Let's talk about the stiff problems. So it was observed by Curtis and Hirschfelder on 52 that explicit methods failed for the numerical solution of ODEs that model certain chemical reactions. So they denote stiffness for chemical reactions which the rapidly reacting components arrive in a very short time in their equilibrium, and the slowly changing components are more or less fixed. That is stiff. So in 63, Dahlquist found out that the reason for the failure of the explicit Runge-Kutta method is their bad stability. So let's see some example. So we have some component A transforming into B, which is being transforming into C. But then suppose that K1 is way smaller than K2. So in the beginning, A is like fast transforming into B. But then for B to transform into C, it will be more slow, okay? So it means that the time scales of the reactions are different from each other. So if we plot the solution for K1 equal 20 and K1 equal 20 and K2 equal 1, so this is as we saw before, this is a linear system, so we can have the solution analytically. So if plotted with K1 equal 20 and K2 equal 1, what we see. So A is like decreasing really fast and transformed into B. But then for B to decrease and transform into C is really, really slow, okay? So as we can see here, the slope for A is like almost infinite, tends to infinite, right? Almost 90 degrees. So if we take some time step, some fixed time step, imagine that we get some time step like this, okay? So we already missed what happened to A, okay? And then we could also just like put really small time step, but I don't know if computationally how long it would take, and maybe it is even outside of the stability region of the method that you are using, and because the K1 is too big, so this K1 is too big, and it's not feasible computationally to find a K that gives you solution on time, okay? So the idea is, instead of it, try to find some or develop some numerical method that can deal in a better way with this kind of systems, which is called a stiff system. So now suppose that on time t1 we introduce a perturbation by adding more A. So the solution behaves like this. So A is like really fast, and we don't have A before anymore, and then at time 1 we add more A here. Let's compare it. So then B, you also have some increase here, but we see that C won't change and almost not change, okay? But more than that, before our C, the steady state was, I can't read it, 0, 1, 2, 3 at 4, okay? So it was reaching some steady state at around 4, and now 2, 4, 6, 8, so it's like around 8.5, okay? Around 9, let's say 9, okay? So some small perturbation on A change the steady state of C drastically, okay? So the A introduced is rapidly converted into B, some fast transient response, and then is slowly converted from B to C. And after the rapid transient, the solution is again smooth, but the steady state of C is higher than before. So this is some characteristic of this system. So it's not like nothing related to the numerical method. So it is some characteristic intrinsic of the chemical reaction that we are modeling here. So yeah, that's it. So stiffness causes numerical difficulties because any finite difference method is constantly introducing error. So it's like the numerical method is introducing perturbation on the concentration, so then it can give some wrong approximation for the real solution. So the local truncation error acts as perturbation of the system, moving the computed solution away from the smooth solution expected. So the difficulty arises from the fact that many numerical methods are unstable in the sense of absolute stability, unless the time step is small relative to the time scale of the rapid transients. So, as I said, so we have some rapid transient here. So we would have to have some really small time step here, okay? So unless the time step is small relative to the time scale of the rapid transient, which in a stiff problem should be much smaller than the time scale of the problem. So this means that we should have some k for stability that is weighs more than k for accuracy, okay? That is, the time step for stability is much smaller than time step for accuracy. So you can see the section 7.5 from the Levesque book. So a stiff ODE can be characterized by the property that the Jacobian matrix, or the derivative of our function, is much larger in absolute value than U line. So if we have some system like this, okay, f of U, so the variation of this function on time, or on U actually, is much larger than the variation of this itself. So U line measures the smoothness of the solution being computed. So it's the slope of the solution, right? Because if the solution is smooth, it's everything okay. so u of t, but if we have some non-smooth behavior, so the slope, so we can have some behavior like this, right? Pa. So in this point, the solution is like this, and then pa, have some discontinuity. So this point is like this, and then jumps to another point. So it's like some steep slope. So U line measures the smoothness of the solution computed, and F line measures how rapidly F varies as we move away from this particular solution. So it's about what I said. So F line of U is like when we look to the linearized system. So when we do some approximation, so if F line of U is big, it means that the system is highly nonlinear, okay? So typically, stiff problems have large Lipschitz constants. So remember that Lipschitz is something like this, right? Some point U star minus F of U smaller than some L times U star minus U. So for this inequality here to hold, that is the variation of F to be smaller than the variation of U is itself, L should be big, okay? So it means that F varies faster than U, and then we would have to, for this inequality to hold, we would have to have some large Lipschitz constant. So the characterization of stiffness. So for systems of ODEs, stiffness can sometimes be defined in terms of stiffness ratio of the system, which is the maximum eigenvalue divided by the minimum eigenvalue. Where so lambda p are the eigenvalues of the Jacobian matrix. We can also write it like F line, but this is a matrix in the case of system. So if it is large, it means that there is a large range of time scales involved in the problem, indicating that the problem is stiff. So numerical methods for stiff problems. So a good method for stiff problems should have a large region of stability. That's why, because we want to include all the eigenvalues in its region, okay? So extending so far into left half planes. Yeah. So that's because usually, as in the example that we have seen before, we had negative eigenvalues, and so they were in this region of the plane, okay? And we want it to extend large because one eigenvalue can be here, and another eigenvalue can be there. So we want that the region get all these eigenvalues to be inside of this region. So usually an explicit method has a bounded stability region. So there are some exceptions, like a Runge-Kutta-Chebyshev method that works well on stiff problems. So some implicit methods have a bounded region of stability, like Adams-Moulton, that are not useful on stiff problems. So on the method that we have seen before, a good method would be the trapezoidal one, that it has the stability region as all the negative part of the plane. And also in the backward Euler, remember, it was the stability region was outside of this circle. But so we could be tempted to say that we are going to approach the analyze this both method, because the trapezoidal could be a good one for deal. We could say that it could deal with all the stiff problems, but we are going to define other kind of stabilities. So we have L stability, A stability. So yeah, we are still going to analyze it better. So usually implicit methods are better to deal with stiff problems. So we want to use a numerical method with a stability region that contains the left half plane. Then in any time step would be allowed if the eigenvalues, we have eigenvalue with negative real parts. So these methods are defined as A-stable. So an ODE method is said to be A-stable if its region of absolute stability S contains the entire left half plane. So examples: trapezoidal, and backward Euler. Another reason that we want the negative real part of the eigenvalues is that, remember, when we linearize our system, the linearized system has its solution for each eigenvalues Vp equal some constant 1 times E lambda 1 T and so on, okay, times the eigenvector here, 2 V's, okay, let's just, so the linearized would be something like this, okay. And if we want to choose, usually we are interested on evaluate the Jacobian matrix around the steady state. Okay, so we want to analyze kind of system in which they have some stable steady state. So usually the chemical reactions, they do something like this. Okay, at some point the system gets saturated and it stops changing over time. So it means that our eigenvalues of this Jacobian matrix evaluated at this point should be negative, smaller than 0, okay? So that's why for stiff problems we want the method to be stable on the left half plane. So we can define some stability function. So if we apply an one-step method to this problem, linear problem, we usually obtain an expression of this form, okay, where Z is equal K lambda. So we can define L stability. So a one-step method is said to be L stable if it is A stable, that is, it is stable on the left half of the plane, and the limit of k lambda of this stability function goes to 0. Okay. Because if it doesn't happen, we can get some oscillations. Okay. In the case of the trapezoidal method, it is astable. Okay, but this is not L stable method, so we can have some oscillations. So what means to say Z? No, I think I got some confused here. So so let's see this compare between astable method. So the backward and trapezoidal methods, they are astable. The point at infinite lies on the boundary of the stability region of the trapezoidal method, but it lies in the interior of the backward Euler. So for the backward Euler, our RZ function is given by this, and the limit of z going to 0 is, or to infinite, is 0. So it means that the boundary of the stability region for the Euler, backward Euler, lies inside, so it is a bounded region, and for the trapezoidal it's unbounded, so it's equal 1. So for this purpose, a method like the backward Euler will perform better than the trapezoidal method. The backward Euler is said to be L stable. Have a look at the section 8.3 of the Levesque book, I think. So as a science homework, I want you to consider this system and simulate it with k equal these values here, considering these initial conditions. And I'm going to put this slide at the OLAP platform, so you can download it and do this activity. Okay. So here the reference tree that I said before is this link. So everything will be at the OLAT platform. Okay, see you on next week.